4.2, day number 2, concavity and inflection points, as well as the second derivative test. Goals are to know and apply the first derivative test, which is review, and to use the second derivative test for concavity and points of inflection. Know and apply the second derivative test. So, as class opener, state the min-max theorem, or max-min existence theorem, including the conditions that must be met to use this theorem. So a function that is continuous, there's requirement 1. On a closed interval, requirement 2 has an absolute max and an absolute min on that interval. For sure, we'll have an absolute max and absolute min. Remember, we would test critical values where the derivative equals 0 as well as the endpoints. All right. What if we don't have a closed interval or a continuous function? How are we going to determine if the function ever achieves a max or a min? Will there be any guarantees? If it's not a closed interval, well, we'd have some other work to do, which we'll look at in the lessons to come, as well as if it's not continuous. Well, if it's not continuous, then there won't be a absolute max, potentially won't be an absolute max or absolute min, depending on how the function is oriented. So the first derivative test, this is review, just tells us that at a critical point, if f changes from a positive to a negative slope, right? So if f is increasing up to a certain point, and then its derivative or slope changes, that's a max. If f changes from negative, right, our second example, f prime is 0 is f prime equals 0, and then f prime is positive, then we have a min. If f does not change sign at c, f prime, right, so let's say the derivative is less than 0, and then it levels out, and then it's still less than 0, there would be neither a max nor a min at that point. Concavity and inflection points are similar. If f double prime equals 0, or is greater than 0, what that tells us is that we've got a function that is concave up on some interval. What do we know about f prime of x? Well, if f prime of x equals 0, like at this point, f prime of x equals 0, we've got a minimum value there. Okay? Therefore, on either side of that, over here on this side of that, we'd see that f prime of x is greater than 0, and on the other side, we'd see that f prime of x is less than 0. So where f prime of x equals 0 and the second derivative of f of x is greater than 0, we've got a minimum value. Okay. Now if f prime of x is less than 0, we'd have the opposite situation. Of course, here f prime of x would equal 0. Over here, we'd have f prime of x is greater than 0. And on the right side now, we're just flipping this image. It would be less than 0. Okay, inflection points. You need to verify that the point is on f of x. Okay, so the point where a graph changes concavity is called an inflection point. So an example of that, right, it's got a change in concavity. So I think we can agree that the function would be concave down on this interval, and then at that point it changes to concave up. So this point right here would be a point of concavity, or excuse me, an inflection point. That'd be an inflection point. Okay, a second example would look like such. Again, concave up here on the left side until this point, which also is an inflection point, and then concave down from there on out. Now, inflection points have two requirements. The first requirement is that f double prime of x, whatever that x value is we're looking at, needs to either be 0 or does not exist. And the second requirement is that f double prime of x changes sign on either side or at that point x. So at each of these two blue points here, f double prime of x would equal 0. And then it changes from a positive second derivative to a negative, or a negative to a positive. Okay, so on this slide we've got the second derivative test. Consider the three graphs below. The red one is f, the blue one is f double prime, and the green one is f prime. The max value of f, which is located right here, I would expect my second derivative to be negative because the graph is concave down at that point. So again, I would expect my second derivative to be less than 0. At the min value, which is located right here, I would expect my second derivative to be positive due to the fact that a min value would imply that the graph is concave up. At the point of inflection, what would f double prime be? Right, our point of inflection would be here. I would expect f double prime to equal 0. Right, so f double prime equals 0. Alright, so at this point, whatever x is, let's say negative 3, I'd expect my second derivative to be negative at x equals, let's say, I don't know, 1/2 or close to. Second derivative would be positive. And again, at our point of inflection right here, I'd expect the second derivative to be 0. The second derivative test says, if f double prime is equal to 0, right, and I'm sorry, if f prime is equal to 0 and f double prime is less than 0, then f has a local maximum at x equals c. Alright, if f prime is equal to 0 and f double prime is greater than 0, then f has a local minimum at c. This test requires us to know that f double prime, we only need to know f double prime at c itself. We don't need an interval. We just need that value. Alright, so using f prime and f double prime to graph f. Okay, so here's f prime of x. Let's identify where the extrema of f occur. So the extrema occur where the derivative equals 0. So 4x cubed minus 12x squared equals 0. Therefore, I'm going to pull out a 4x squared, and I get x minus 3. So I know that the extrema, or the critical points, exist when x equals 0 and when x equals 3. So I can do a nice little sketch here. I know that the derivative, right, equals 0 at 0 and 3. Okay, so I know that f prime equals 0 at 0 and at negative 3, positive 3. So I would probably test f prime at negative 1, f prime at 1, and f prime at 4. Values I would get, this would be less than 0, this would be also less than 0, and this would be greater than 0. So I know I'd have a decreasing function here and here, and I'd have an increasing function here. So if I were just to make a general sketch of f, right, I'm going to make a general sketch of f in blue. I would have a decreasing function where the derivative is 0 there, and I'd have a min, and I'd come up right here. So I see that the derivative is negative, then it's 0 at x equals 3, then it becomes positive. So if I were to sketch that over here, again, my graph of f would look something like this, where this is x equals 0, and this value is x equals 3. Okay, in the next part I want to find where f is concave up, so I'd find the second derivative of f of x. which would just be the derivative of the first derivative, which would give me 12x squared minus 24x. If I set that equal to 0, I'm going to pull out a 12x. That would leave x minus 2. So the second derivative would be 0 when x equals 0 or 2. Okay, so again, testing here, I know that f double prime is equal to 0 at 0 and 2. If I were to test values around it, I'm just doing this on the side, I would see that I get positive values in between negative infinity and 0, and then from 2 to infinity, and I get a negative value if I were to test, say, f double prime of 1. Alright, so what exactly does that tell us? So that tells us that we would be concave up on these intervals and concave down on this interval. So let's go ahead and again graph a sketch here of f, possible graph. Okay. Let's take what we had earlier. Okay, where here I have x equals 3, right? We knew that the first derivative, right here, the first derivative of x was 0 there, and it was also 0 there. Okay, and x equals 0 and x equals 3. The second derivative allowed us to know that we're concave up here and concave up here. Oops, I'm sorry, and concave up here. And this right here is a point of inflection where x equals 2. And in between there, we're concave down from 0 to 2. So a general sketch based on the derivative and the second derivative. Okay, so here I've got one more example. Find increasing, decreasing, and concave up, concave down, as well as inflection points. Okay, so first of all, let's start increasing, decreasing. So the function would be increasing on the following intervals from negative infinity to 0, as well as from 1/2 to infinity. Right? I took that directly from where the first derivative is greater than 0. It would be decreasing from 0 to 1/2. Okay, it'd be concave up. Concave up from, it looks like 1/4 to infinity. And it'd be concave down from negative infinity to 1/4. And the point of inflection, or inflection point, there's only one of them, would be at the value x equals 1/4 and y equals, I'm not going to do it, but f of 1/4. You can calculate that one on your own. Alright, I believe that would be it for this lesson. This is 4.2, day number 2 on the concavity inflection points second derivative test.